In the last lecture, I talked a lot about this idea that you can cool the atmosphere off, and that leads to the formation of clouds and precipitation. It begs the question, though, how do we cool the atmosphere off? Well, the obvious way is just through radiation heating and heat loss. But it turns out there's some really other important ways that the atmosphere is cooled to the dew point, which causes clouds and precipitation. And that's through atmospheric lifting, which we're going to talk about. We're also going to talk about atmospheric stability, which is a little bit of a complicated concept. You might have to take a little bit of time to work on it outside on your own, looking at the textbook and the diagrams that are there, but this should get you started on it. So let's first off talk about how we can lift the atmosphere up and what that does. The important thing to note is that when we do lift the atmosphere upwards, that parcel of air, and here we're going to talk about sort of a theoretical parcel of air that behaves within the broader environment, it expands because there's less atmospheric pressure on it. And when a gas expands, it cools. When we compress a gas, it heats. In the atmosphere, though, there are many opportunities for the lifting of air that leads to what is called adiabatic cooling. That adiabatic cooling I'm going to talk about more when I talk about stability. For the time being, let's imagine that we can find different ways to lift the air up and cool it. What are those key ways? Well, the one that I think is easiest to understand, and so I'll start with that, is what's called orographic lifting. If we take air and we push it up and over a mountain or a mountain range, the air, because it's forced to go upwards, expands and it cools adiabatically, and that leads to the formation of clouds and precipitation. This map on the next page shows the process of orographic precipitation in the state of Washington. Puget Sound and the Seattle area is right through here. We often hear how rainy Seattle is, but the reality is Seattle's in a relatively dry area. There are a lot of cloudy days and light rain, but far more rain falls on the Olympic Peninsula to the west because of the Olympic Mountains. What each of these diagrams show right here is the amount of precipitation. The blue lines show how much precipitation falls in each month. And then on the map, the areas in dark green show the areas that get the greatest amounts of precipitation, and the areas in red show those places that get the least amount of precipitation. And what we can see on the map is because winds largely prevail from the west to the east in Washington state, the mountains in the Olympics get the greatest amount of precipitation by far. The air then falls on the east side of the Olympics, and as it does that, it compresses and it actually dries out. So this is actually a relatively dry area. The air then gets pushed up over the Cascades, and we can see again a belt of large amounts of precipitation, though not as great as the Olympics. Then it falls on the east side again, and as it moves across the eastern part of Washington, the air is quite dry. This shows the windward side of a mountain range getting a lot of precipitation orographically, and the leeward side being relatively dry. That's a classic example of orographic precipitation, and it happens lots of other places as well. In fact, in south central Alaska, we see a lot of this taking place around Prince William Sound, where there's a lot of precipitation that's caused orographically, leading to huge amounts of precipitation in places like Whittier, and even not far from Whittier, Girdwood. But by the time you get to the leeward side of the Chugach Mountains in Anchorage, there's a relatively small amount of precipitation compared to those much wetter areas. Another way that the atmosphere can be lifted is through convection. And this is sort of a strange one. When we heat the air up, usually because we've got a lot of nice sunlight warming body of land that heats very quickly, the air down near the ground gets more buoyant because it expands. And as it expands, it's lighter, so it goes up. And as it goes up, it cools. So strangely, heating leads to cooling. And this commonly happens, especially in places that are continental, where there can be a lot of that extra heating in the ground. We're going to get back to convectional lifting because it's pretty important in understanding instability. We can also have lifting taking place in convergence, like the intertropical convergence zone that we've talked about, where the trade winds come together. And then we can also get lifting occurring along weather fronts, where cold air pushes into warm air, and as a result of that, the warm air gets pushed up and above it. That's really important in the weather that takes place in and around the subpolar lows, as we'll talk about in the next lecture. Now, the next thing to talk about is the notion of atmospheric stability. Atmospheric stability is something that is particularly important to understand why there is severe weather and why clouds often have that very puffy or cumulus form to them. But before we understand atmospheric stability, we have to talk a little bit more about the adiabatic lapse rate and also the environmental lapse rate. The adiabatic lapse rates are those rates that take place when we take a parcel of air that's being lifted up orographically, through convection, through any other of the forms of lifting, and it gets pushed up in the air. That cooling that takes place is fairly regular when the conditions are dry and there's no condensation taking place, meaning that there is no cloud formation. It's called the dry adiabatic lapse rate, and it takes place between around 5.5 degrees Fahrenheit for every 1,000 feet you lift a parcel of air. That slows down considerably once condensation takes place, because condensation starts to release that latent heat that we talked about before. It takes less energy to have a particle of water in the atmosphere than water vapor. So energy is released during the condensation process. So once you start to get into cloud area, that adiabatic lapse rate starts to fall off, depending on how much condensation there is, somewhere between 2 and 5.5 degrees Fahrenheit for every 1,000 feet. Now, if we imagine that air that's being lifted up is a discrete parcel of air, which is sort of a strange concept, but it helps us understand stability. And then we compare that adiabatic lapse rate to the general environment, what's happening around that parcel of air. We can compare the adiabatic lapse rate to what's called the environmental lapse rate, which is highly variable. Sometimes the ground is actually warmer than it is in the upper atmosphere. Sometimes the upper atmosphere is a lot colder than it is compared to the adiabatic lapse rate. If we can then compare that parcel of air to the environmental lapse rate, we can understand whether or not we're going to have stable air or unstable air with puffy cumulus clouds like this. That helps us to understand a little bit, at least, of why when we fly through a cloudy area, we feel all that bumpiness taking place, because the air within it is unstable and wants to move. So let's talk about instability a little bit. Instability takes place when the environmental lapse rate is greater than the adiabatic lapse rate. That means that the temperature in the general environment is cooling off more quickly than any air in a parcel that's being forced upward is cooling. If we take a look down here at this chart, or at this chart over here, it gives some examples of this. Here's the environmental lapse rate of the surrounding air temperature. Here is the air of that parcel that's being lifted up. Because the adiabatic lapse rate is less than the environmental lapse rate, what happens is that parcel of air is always warmer as it goes up, up, up. And because warm air wants to rise, it means that the air is unstable, and the parcel is buoyant, and it has an inherent nature in it to go upwards until it mixes with the environmental air all around it. That's the classic form of instability, and it leads, when clouds are being formed, to puffy clouds or cumulus clouds, as we've talked about before. The classic conditions of instability take place on a nice, warm, sunny day, especially in the springtime when the air is still relatively cool up high and the ground down below is starting to heat. It makes a steep environmental lapse rate, and then any parcels of air that are lifting upwards have a tendency towards instability and buoyancy. And before clouds start to form and the instability is too great, it makes a good day to go paragliding. And this is a GPS track from a friend of mine who walked his way up to the top of Flat Top and then jumped off with his paraglider and moved down slope, doing loops as he went, using the inherent nature of unstable air that's pushing upwards to stay as lofted as possible for as long as possible. That's unstable air. Stable air is just the opposite of this. The environmental lapse rate is now less than the adiabatic lapse rate. And that means that any air that gets forced upwards, lifted upwards, is actually colder than the air that surrounds it. And so it doesn't want to be buoyant. It doesn't want to go up. It forms stratiform clouds, as you can imagine, flat gray clouds. So here's a parcel of air that's being lifted and forced up and over one of the big mountains in the Cascades, one of the big volcanoes. It's being lifted up orographically, so it has to go up, but it doesn't want to go up in terms of its stability. So as clouds are formed, there are these stable, stratiform, cap-like clouds that form. Some of the classic examples of stability take place in south central Alaska in the middle of the winter, when it gets very cold and all the cold air starts to settle into the low areas. And we get what's called a temperature inversion, where the temperature is actually warmer up high than it is down below. That means that any parcel of air is going to have no tendency to move upwards. When we get fog forming and cloud forming, it's often down in the lowland areas, as we can see right here, because that's where the air wants to sit, and because it's cold, it reaches the dew point and it forms fog near the ground. So that's the idea of stability. Again, it might take some time to think about, sort of wrap your head around. You will want to take a look at these diagrams a bit, but it's very important for understanding just sort of on a day-to-day basis why we have fog, why we have a bumpy airplane ride, why we see puffy clouds versus flat clouds. And so I think it's inherently a very important part of understanding the atmosphere in this course.